Good afternoon, class. It's Mark Gastonguay again, welcoming you to the next session in MI210, our webcast on the essentials of population PK/PD. Our topic today is going to be focused on data requirements and data formatting. But before we move on to the new topic, I was going to address one or two of the questions that came across the discussion board over the last week. It seems to be that this discussion board is working out pretty well. We're getting, a reasonable amount of traffic here and some good communication. I'd appreciate your feedback on this, whether or not you think it's useful or not, and how we might be able to make it more useful if it isn't. But it seems to be working pretty well so far. Now, there was a topic this week, actually various topics. I'm going to pull that up, and we'll review that as a group. And these are some concepts related to the first couple of lectures. The first question was, I said something like naive averaged analysis can be problematic because when you average across data, the skewed data are not usually normally distributed, and the average doesn't always represent that central tendency. And that's true in PK data. For example, if you're taking the average of observed data, we know that the variability, even if it's just at the individual level, but the variability is higher at the peak concentrations than it would be at the trough. And so your reflection there of just taking a raw average is probably not accurately reflecting the concentration time curve if you take the raw average at each individual data point, not accounting for the differences in the residual variability or the heteroscedastic nature of the data. And so what you'd end up with is a mean concentration time curve that's not really reflective of the expected value of the population. It would just be the means at each data point. Another problem that can arise is if you have an imbalance in sampling. For example, if you have some individuals whose concentrations have reached below the quantitation limit towards the latter part of the concentration time curve, and now you take an average across that. Now, depending upon how you impute those, if you impute them at zero, or if you use the last observation carried forward, or if you just drop them and take the average of the remaining subjects, any one of those mechanisms is going to result in a biased estimate of the mean at each of those time points. And so that's another problem with the naive average data. It's when you have imbalance in the design. Like I said, I think it's probably easier and not any worse to just do a naive pooled analysis if you're looking for a quick initial estimate. But I think we pointed out that the correct way to analyze that is to use a full population nonlinear mixed effects model. Next question is, in a heteroscedastic variance, how do we assume that the variance changes with concentration, but we end up only estimating one sigma value in the model? Well, remember when we worked on that nonlinear regression spreadsheet with the extended least squares regression, we had a single sigma to be estimated, but that sigma was related to the predicted concentration. So in fact, the denominator there was something like the square root of sigma times the prediction. So there's a single sigma term, but that sigma term varies from point to point. I'm sorry, the denominator of the objective function varies from point to point because of the dependence on the prediction, which is different from each point to point. So there's a single random residual variance, but there is a deterministic component of that which is related to the prediction, and therefore the variance at each time point is different, even though there's one single sigma variance across the whole data range. And then that's related to part 3 here, where the question is, what does it mean when we say that we can estimate the functional relationship between sigma squared and the model prediction? We can estimate that as part of the modeling process. So in the extended least squares analysis, or the maximum likelihood objective function, we specified that the variance was equal to sigma squared times the prediction. We could specify different models for that. We could say that variance is equal to sigma squared times the prediction squared, or sigma squared times an exponentiated prediction. That functional form can be modified. We could take the inverse of the prediction if we thought that was a better way to weight the data. So that's what I meant, is that the relationship between sigma squared, where sigma squared is just the random component of the residual variability, can change depending upon what deterministic part of that variance model we want to implement. And we talked about looking at residuals versus pred and weighted residuals versus prediction as diagnostics to help us test the assumptions we're making about the residual variance structure. And those are useful things to look at when we're selecting between different functional relationships there. We'll see this more as we move into the population implementation in NonMem, where the same concepts will arise, but we'll actually be deriving different structural forms for the relationship between the residual variance and the model prediction. Okay, I hope that answers those questions. If there's follow-up necessary, please continue to post questions on the discussion board. So I'm going to move on to our topic for today then, and that is the population PK/PD data requirements and formatting. So we started out with our simple case here. We've got a couple of exposure-response relationships, but remember, what we're also interested in is modeling the pharmacokinetics of our phase 1 data set. And so before we get into developing those models, we've got to create the data sets and make sure they're formatted correctly so that we can communicate the appropriate dependent variables and predictors at each time point to the modeling software. So by way of overview here, we'll start off with reviewing some of the data terminology. And I'm going to give you a brief introduction to the NonMem software, and I'll explain why later. We'll talk about requirements for NMTran, which is part of the NonMem system, and the formats necessary there. And then we'll spend some time discussing data assembly points to consider and best practices. This is where you really need to put some thought into the data assembly process, and oftentimes where some of the stumbling blocks are in analyzing data sets from routine clinical observations or from drug development trials. We've got a couple of practice problems to work on and then some study guide questions. Okay. Well, let's just review some terminology. Some of these terms we've already addressed before. Remember the dependent variable, that's that quantity that we're modeling. In a PK model, it's the observed concentration. But it can be a multivariate endpoint, and we discussed how that might translate to modeling correlated residual error, for example. But a multivariate endpoint I'm talking about where we have two dependent variables measured at the same time. Concentration and defect in a PK/PD model, maybe parent and metabolite in a multi-analyte model. So the dependent variable can be a multivariate endpoint. And also want to point out that it's sometimes useful to use a transformation of the observed scale, such as a log transformation, which we might do to implement an exponential residual variance or a log normal residual variance. We talked about that the last time. And sometimes another transformation is used, like a logit transformation, where we're taking maybe a continuous variable that's measured on some sort of a capped scale, where there's a lower and upper bound, and we want to make sure that the derived variables, the model predictions, simulations from that model are also constrained to that same scale, so we might use a logit transformation. But whether or not we decide to use a transformation, it's that value that is a dependent variable. Now, the independent variable, as we discussed earlier, is really the basis of the model prediction. These are the known or observed quantities that we can measure and that serve as the primary predictors. In PK, that would be dose and time. Keep in mind that in regression models, the independent variable is assumed to be known without error, or with a much smaller error, or much better precision than the dependent variable. This is something we'll discuss as we get into some of the PK/PD modeling discussions, but it is quite important when we're trying to relate one predictive variable to a dependent variable. We've already discussed covariates, in that these are known or measured variables which are predictive usually of individual differences in parameters in response. And the rest of the terms here, repeated measures, longitudinal, sparse, and extensive, those haven't changed since the last time we discussed them. We're talking about the types of data sets that we're typically using in population PK/PD. They're all characterized by repeated measures within subject, usually over time, longitudinally, and oftentimes we're dealing with sparse data. Okay. Well, we've been trying to cast this course in the context of learning population PK/PD and not necessarily just learning a particular piece of software. However, it's very handy here. We use NonMem as our example tool throughout the course, and it's very handy, especially when we're talking about data specification, to use NonMem as an example. It just so happens that the data specification system used in NonMem is very, very powerful, very flexible. It allows us to implement all kinds of data conditions that we would typically encounter in clinical pharmacology, therapeutics, as well as drug trials. And in fact, this NM-tran specification, and I'll explain what NM-tran is in a minute, but this so-called NM-tran specification is something that's been picked up by subsequent software tools. So other developers of software have developed to this standard, and so it's become almost a standard specification of data sets for population PK, independent of software tools. There are other specifications used for different tools, but this is the most commonly used one, and probably one of the most complete ways to capture all of the necessary dosing, covariate, observation, and other events that we want to capture as part of the modeling process. So we're going to use NonMem here and the NM-tran system as an example of how to format data. But keep in mind that these principles would apply across other tools potentially. So it's the first time we talk about NonMem specifically. NonMem, stands for nonlinear mixed effects modeling, of course, but it's comprised of multiple components. And this is not always appreciated, but there's, originally there was the development of this algorithm for nonlinear mixed effects, which was called NonMem, and that was the core estimation algorithm in what we now call the NonMem system. The NonMem estimation core didn't have any fancy interfaces for specifying model structures or data sets. It was really just some Fortran code to do the parameter optimization in a nonlinear least squares mixed effects model. There, at that time, to communicate the model structure, the user had to supply a prediction routine, or also known as a pred routine, and that's still possible to be implemented these days, but not likely. What we use now to communicate with NonMem is something called NM-tran. NM-tran stands for NonMem translator, and what this does is it converts a relatively user-friendly model code, which we call a control stream, and a data set to the NonMem fixed format Fortran code. And the two bits that the internal NonMem uses are things called fcon and fdata, but these are not in formats that we would like to specify as end users. So we use NM-tran, which is sort of wrapped around NonMem, to communicate the model structure, the parameter estimates, the estimation methods, all of those options that we'd like to select, as well as the data contents and special instructions for data handling. Okay. So the data set itself is an ASCII text file, as is the control stream, which is the way we specify the model code. And for the model specification, we have two options under NMTran. We have something called a $pred model, and this is a simple algebraic model specification. So as long as you don't need any reverse or any recursive dependencies on prior solutions, as long as your prediction can be made directly from any variables observed at the same time point, you can use a $pred model. This is commonly used for simple algebraic models like a linear model or an Emacs pharmacodynamic model, and also for some of the probabilistic type models such as a logistic regression. We'll use a $pred implementation. But for those cases where you want to analyze a compartmental model for population kinetics, that's where we want to make use of the PredPP prediction specification. PredPP stands for Prediction for Population Pharmacokinetics. This is really a library of models, and in NonMem 7 there are 13 different libraries that 13 different elements you can choose from this library, each of them specifying a different type of model. We'll look at those in the next week or two, but just suffice to say that there are two different ways to specify the model, and your choice of that model specification will impact the way that you create the data set and the format that you're going to be required to meet for each of those. So NMTran also allows us to specify a data set. This is an ASCII text file that is converted to a fixed format Fortran file, and we communicate then the contents and names via a couple of control records in the control stream. I'll discuss those in more detail later. But the basic idea here is that we're using this translator program, NMTran, to get the data and the model code from a relatively user-friendly type implementation to something that is much more cumbersome but is required for use by the underlying NonMem estimation core. Because of its facility to deal with the types of data sets that we're commonly faced with in population PK, we often call these data sets NMTran data sets. And that has become sort of a recognized standard, an NMTran formatted population PK data set. So that's what we're going to study a little bit now, and we'll look at several examples of how to create those. So NMTran has its own language as well, and this is not uncommon to other data management terminology. But it divides a data set into columns and rows, where the columns are known as data items and the rows are known as data records. Okay. Regarding data items, well, this is really just the name or the value corresponding to a particular heading or column in the data set. So this is the label we're going to attach to a data item so that we can call that value as part of the prediction model, or also to define which column is the dependent variable. Now, there's some big advancements in NonMem 7 compared to NonMem 6 and earlier versions with respect to data specifications, size limits, and so on. Previously, you were limited to 20 data items, but now NonMem 7 allows you to include up to 50 data items at one time, which is quite handy. So that means you have 50 data items included as part of your model in some way or another. But the actual underlying ASCII data set could include many more items that can be dropped or ignored for a particular run. So your actual data set could have more than 50 columns. So maybe you could have 150 columns as long as you drop 100 of them, and you're only limited to 50 moving forward as part of the model prediction. So that's a good increase in that limit makes it much more feasible. With a 20 item limit, there were many cases where we were running into challenges and trying to implement models with multiple predictors. The data records now, these are the rows in the data set. Each row is known as a data record. And rows have specific meanings. And you'll see as we specify data formats, especially for the PredPP type, each row has a unique purpose. And each row describes a unique event, such as a dosing event, a PK observation, maybe a change in a covariate value. And each one of those is represented by a single data record. Now that's applicable to PredPP. In $pred, we'll see that you can carry forward 2 bits of information or more on a single data record, and that's unique to $pred. But we'll look at some examples that will differentiate between the two. But in general, this idea of data records is quite important when we're dealing with the recursive subroutines in PredPP. Used for predicting compartmental concentrations in population PK models. Okay, next let's talk about some general data requirements. Well, the data sets, as I mentioned, were ASCII text files. Well, there's some more specificity to that requirement. First of all, if it's a population model, all data records for an individual must be contiguous. That means that if you have individual number 12 in your data set, that individual's records should all be contained in a contiguous block of rows. If you have some of individual 12 near the top of the data set, and then you have some individual 12 near the bottom of the data set, that ID will be recognized as 2 separate individuals. So you want to make sure that they're sorted by ID. On top of that, the data set is a simple ASCII text file that could be space or comma delimited. No tabs, okay? And this is a relatively straightforward format. Comma-separated files are quite useful sometimes. The one thing you've got to look out for with either space or comma delimited is if you're pulling data in from a clinical database where there might be a comment field. Sometimes that comment field may have commas or spaces within the field, and that could throw a wrench into your alignment of data records. But we'll discuss some solutions for that later. Each data record must have a placeholder for every data item. So you've got to have something included. This is a flat table file, and every cell in that table has to have some placeholder or value. If it's a null value, you can use a period or 0, and sometimes 0 has a specific meaning of 0 as well. So you've got to be careful about that. But the rule here is that every cell has to have some data value included. We can comment out data records, a whole row, although you can't comment out just a single cell in a data set. So the comment applies to an entire row of a data set. And that's sometimes useful when we want to eliminate potential outlier data points or to subset the data. We might just comment out certain records. The data values themselves are numeric characters. We can include the comment indicator, which can be non-numeric, and placeholders, of course, we can have a period. The other exception to that is that if we use a PredPP data set and we're using calendar date and clock time, the slash or the colon separators can be used in those fields. But all other fields require numeric values. So that means if we have covariate factors that we want to code, for example, we might have male and female sex in our data set, and instead of coding them as alphabetical characters, M, F, we would have to map them to a numeric value, maybe like a 0 or 1. And so NonMem doesn't directly recognize the alphabetical type characters. We've got to map them in our data preparation ahead of time to a numerical value. Let's see what else. So numerical values here can be much longer than they used to be. Now we can have up to 24 characters in the data value, except for the ID column, which can be up to 14 digits long, which is an extension. Both of these numbers are extensions over the limits that were imposed in NonMem 6 and earlier. I believe it was 16 and 6 in the past. Now we're up to 24 characters long for the data values and ID values up to 14 digits long. That's helpful if you have some subject IDs in your clinical data set that are, maybe a composite of site, study, and investigator, and so on. Sometimes they can get quite long, so 14 digits gives you some flexibility there. Of course, you could always map it back to a different value, a unique number that might start at a smaller scale from like maybe 1 through the number of individuals you have, and carry along that longer ID as part of your source data set, but that would have to be dropped if it was longer than 14 digits long. Okay. The other important point here is that users specify different NMTran data formats depending upon the type of model subroutine. You'll see this in the examples. It's important for you to understand. The $pred data format's quite simple. This is a place where it's pretty much you match up on a single row predictors and observations. There's no dependence on some prior prediction or carrying forward superposition of a population compartmental PK prediction. There's none of that involved. It's just a direct prediction based on a single row of data. So it's difficult sometimes to deal with some of the observational type data using $pred, and we'll only use that for the algebraic type solutions, simple single dose PK or non-PK type models. When we get into multiple dose PK, especially in a population context with superposition of or carryover of concentrations from one record to the next, that's when we need to use the model library, the PredPP, and then that does change the way that we code the dosing and observations. Okay, so there's some required data items. We'll get into some specifics now. The NonMem estimation course, so this is the base level. This is what's required for a population model. Well, for individual data, let's start. We need something called a dependent variable and a missing dependent variable. I'll define those in a minute. And in addition, if you're doing a population model, we need an individual ID to indicate subjects. There's something called the L2 data item, which is optional. This is related to the covariance of the residual error that we discussed when we were talking about the sigma matrix, the off-diagonal elements in the sigma matrix. This really only has to do with a multivariate endpoint where there might be that sort of correlation. And we talk about this in the MI210 course when we model parent metabolite data simultaneously. We're not going to talk about it in this course, but just be aware that there is a data item available for us to access that sort of a correlation. And NMTran is smart. It will impute default values for some of these things, and I'll explain what those are. So let's define these. DV, this is a recognized data label by NMTran and NonMem. This is the dependent variable. This is the column that includes the data to be modeled. Now, if you're going to use a transformation of the data, let's say you're going to take a log transformation of your original scale. Well, you might want to do that transformation, but the column will still be named the DV because now you're modeling as the dependent variable the log transform value. The MDV column represents a flag for missing dependent variables, and this takes the usual 0-1 nomenclature where 0 is not missing and 1 is missing. And this is simply used to specify where the dependent variable is present or not present on a given data record. This can be handy if we have missing data and we want to establish some modeling method to adjust the likelihood function for the missingness. It also is handy just in coding which records are those that include observations versus those that are just a change in a covariate or maybe a dosing record. So MDV is 0 for any data record where the dependent variable is present and observed. The ID is also a recognized value. That's the individual identifier. It's also known as the L1 data item for population models. If you're reading some of the hard copy NonMem manuals, you'll see this thing called the L1 data item. Well, that's another word for the ID. This is the first level in our mixed effects hierarchy, and it's the individual ID value that we use, and that really drives our grouping estimation for the individual random effects, the ETAs in NonMem language. And then the optional one, L2, which we mentioned before, the level 2 indicator. This allows us to identify records that might be correlated at the residual level. Again, reserve that for multivariate endpoints and another course. So now, moving on to specifics for $pred or user-written pred. In those cases, the only data items that are recognized are the ones that I've just discussed: dependent variable, MDV, ID, and L2. For a population model, you've got to have at least the ID and dependent variable. The missing dependent variable will be imputed automatically, and the L2 is optional. All other data items in your data set are going to be defined by you, the user. They have no special meanings. It would be useful to avoid some of the other reserved names that we'll mention later, and we can look at different data items that you could use in the PredPP type models. It's probably good practice to avoid those names, and also to avoid names of model parameters. But other than that, it's wide open. You can name these values following certain nomenclature conventions. Anything you'd like. Remember, the $pred model is not recursive, so there's no, in a multiple dose PK system, for example, there's no carrying forward of the compartmental prediction from one time point to the next. So a record, it must contain all the necessary data items for the prediction calculation. And then the general rules that we already discussed also apply here. So let's look at a simple example of a $pred data structure. So we're going to use a pharmacokinetics system here, and it's a single dose IV bolus model. And we have concentration at time t described by dose divided by volume times an exponentiated clearance over volume times time. So your typical IV bolus equation. What are the independent variables here? Well, we've got dose and we have time. Model parameters include clearance and volume distribution, and the dependent variable is concentration at each time point. So our data records for $pred have to reflect each of these components, except for the parameters, of course. So our dose here is a single IV bolus of 100 milligrams, and we have concentration observations at 2 and 6 hours post-dose. So this is just a snippet of a data set, sparse sampling with 2 individuals. So here's what it might look like. We have a comment column. The comment column really is not required, but it's kind of handy to use if you put this in as the first column in your data set. Then we can easily comment out a row by just adding a comment indicator in this cell for the row to be eliminated. But the required items here, ID and DV, are present. Okay, so the ID is the individual ID. So we have 2 subjects here, subject 1 and subject 2. Each one of them has 2 observations. Time here is not required for NonMem purposes, but it is required for our model because time is part of the model equation. So we have time 2 and 6. This is relative to some nominal dosing time at time 0. And it's a single dose implementation here, so we're going to carry forward our dose because, of course, in order to make this prediction of concentration at time t, we need to know the original dose and the elapsed time. And so that's what we've got here. We've got the original dose of 100 milligrams and the elapsed time of 2 hours. We have an observed value of 24 concentration units, milligrams per liter. And so we need to make a model prediction for that. Okay, the next time point is 6 hours. And that dose is, again, 100 milligrams. This is the same original dose. Remember, this is not a multiple dosing setting. We're just using this exponential IV bolus model to describe the prediction at determined time points. And we have an observation recorded there. When we switch to the next individual, you see the same sort of setup, different dependent variables, of course, because there are different observations for this individual, but same idea. Now, so a couple things to remember is that all the records for an individual are contiguous. So all of the rows for ID number 1 are grouped together, and then you move on to the next subject, ID 2. They're sorted, in this case here, in time, although that wouldn't absolutely be required for $pred, but it is a requirement for pred PP. But the other requirement for $pred is that everything we need to make the model prediction is present on a single row here. So all of these values here, the ID, the time point, the dose, and of course the dependent variable, they're all present on a single row. There's no dependence on a prior row or a subsequent row to support the model prediction. So this view here in the table is similar to the way it might look if you imported a comma-separated file into a spreadsheet. Or if you looked at it in a text editor, here I have it opened in Notepad, you can see that it's just a simple text file with commas between each field. So the placeholders are there in every cell, and there's a comma separating each field. So a text editor is not the most visually appealing way to look at this. It's just presented here to illustrate what exactly is in the file. The text editor just tells you in plain text what's here in this file. When we import it into a spreadsheet and we select a comma delimitation, it will be spread into fields like this. I would recommend, I think comma delimited text is probably the most useful way to deal and interact with the NonMem software. It's also very useful for interacting with other tools such as R, WinBugs, and so on, and it's easily readable and writable. Okay, we'll shift gears now and discuss the real value of NMTran, and that's the interaction with PredPP to accommodate a much broader range of models, data sources, data types, and we'll illustrate a few of those as we move along here. Okay. So in PredPP, we've got a library of PK models with all types of input possibilities. Single or multiple IV or oral doses. We can have zero order infusions, steady state doses or infusions. We can have irregular dosing intervals, irregular observation times, multivariate observations of 2 types of DBs at the same time. We can have covariates that change over time, and any combination of these, plus almost anything you can think of. This was really designed to deal with the type of heterogeneous type data that you observe from medical records, either in clinical practice or in typical observational PK collections in clinical trials. Not necessarily the very rigid phase 1 type designs, but this allows us for the flexibility to accommodate the other kinds of observational data that you would obtain in later stage development. So what differs with PredPP with respect to data specs? Well, one thing is that there's a tight link between the data set and the model structure. And in fact, sometimes we are coding bits of information about the model prediction or the model structure via the data set. Sounds a little bit odd, a little cumbersome, but it actually, when you use the two together, it can be quite powerful. I'll show you an example of that as we go a little further today. But you'll also find it quite helpful as you do implement more complex models, particularly when you have the need to reset a single compartment or reset an entire system, or to allow for observations from different compartments. This is where the tie between the data set and the model is quite useful. In PredPP, the data sets have a requirement that each record represents a single event. So an event is either an observation, a dose, an other event like a change in a covariate measurement, or a reset. But each row represents a single one of these types of events. You can't have a single row representing both the dosing information and the observation. Okay, this is unique, and it actually simplifies the internal calculations, but it's something you have to be aware of. Of course, if you try to do this, you'll usually get an error message back from the software. So there's a good amount of error checking that goes on with NM-Tran and NonMem to make sure that this rule is enforced. Like I mentioned, we can also reset system amounts to 0, or to turn a specific compartment on or off, and we use data records to do that. The other thing that's unique about this is that this is a recursive subroutine. That means that the prediction of the compartment concentrations, or more specifically the amounts in each compartment, they're advanced from one data record to the next, or from one time point to the next. That's known as a recursive subroutine because that memory of the predicted value from the prior time point has to be carried forward. But the thing that gets interesting here is that when advancing that prediction from one record to the next, the value of the covariates and predictors at a current time t, those are the same values that are used to advance the prediction from time t-1 up to time t. So there's sort of a backfilling that goes on there of the covariate values to the time of the preceding data record. And that's something to be aware of if you have time-dependent covariates and large gaps in time where those covariates might be changing quite a bit. This could be influential in your model prediction for the change in the PK system over that period of time. So we can talk about how to deal with that later today. And then, of course, the other general data requirements also apply. So by the way, all of these data items that I'm discussing in these general terms, these are all described in the NonMem help system. I'm just giving you a flavor for some of the most commonly used ones, and as a way to illustrate how we can construct these data sets and to get you comfortable and familiar with these terms and how we implement them. For PredPP, we've now expanded our list of required data items. Remember, for $pred or just the NonMem core, all we needed was the ID, DV, missing dependent variable, or an L2 optionally. But now when we're dealing with these recursive prediction subroutines that involve compartmental models for PK systems, we need ID and DV. Now, two new ones here, amount and time, are required. And I'll describe each one in a minute, as well as something called EVID, which is the event ID. So we've already defined ID, dependent variable, and MDV, missing dependent variable. Let's describe the others. Event ID first. This is a very useful data item. It can be used to subset your data set, but what its real purpose is to specify the type of event for each data record in a PredPP model. Remember, each data record has a different purpose, a different type. And there are 5 categories for event ID. There's 0, which indicates an observation of a dependent variable. There's a concentration observed at that particular record. for example. One would be a dosing event. So that would specify the amount of dose, the rate, all of those sorts of things. But event ID 1 indicates that a dose is entering the system. Event ID 2 is quite handy. This is other, and it takes on all kinds of uses. Usually it's to turn a compartment on or off, or to change a covariate value when there's no dosing event or there's no observation happening at the same time. And then there's 3 and 4. 3 is a reset of the system to 0. So, for example, in a washout between periods, you might want to use a reset. Or if you want to follow that reset with a subsequent dose, you can use event ID 4, which does both at once. It's sort of the combination of 3 and 1. It resets the system to 0, then follows it up with whatever dosing information is present. So this is one of the core data items. It's only present in PredBP. You're not going to be able to use an event ID data item with a $pred model. But for the PredBP model libraries, it's required. It will be imputed automatically by NMTran to a default value. And the default value takes on 0 or 1. Either it's an observation or it's a dose. And NMTran will figure that out depending upon, do you have a value in your dosing column? Do you have a value in the dependent variable column? And it usually makes the correct guess there. However, the default will not allow you to specify items 2, 3, or 4 for event ID. When you're pulling data sets together, I think it's handy to actually code this manually. It just gets you thinking about what's on each record, and it gives you that flexibility to use some of the non-default items later on. Okay, the AMT or amount column. This is a reserved data item in PredBP, and it simply specifies the amount of drug mass entering the system, the dose. For all of these data items, it's up to the user to keep track of units and make sure they're consistent. So if you have an amount and your parameters, for example, a volume and distribution, if your amount is in milligrams and your volume of distribution is in liters, then your observed concentration is milligrams per liter. It's up to the user to map those. But this is quite simple. It's just an amount. There's also the time column, which is very useful in PK models. The time column identifies the time of an event. It can be elapsed time or observed clock time. So you could have a 0, 1, 2, 3 type continuous variable, which is elapsed from some reference point in time. You could have some clock time. Usually we use a 24-hour clock. So usually so many hours colon and so many minutes. We can also use time in conjunction with date. And that is one case where 2 columns, date and time, are used together to specify an elapsed time, which is calculated internally by NMTran. It's a pretty handy thing to have because oftentimes when you're dealing with later stage drug trials or an observational therapeutic drug monitoring, you don't necessarily have nominal elapsed times. They're just some observation on a particular date at a particular time, and as long as you have that information, you can tie them in and then sort them accordingly. Again, all of these data items are defined with all of the options in the NonMem help files. I'm not intending to replace the help files here with the course notes, but if you have any questions on these or you want to understand some of the specifications in more detail, you can just look up, for example, the time data item in the online help file. Okay, so let's look at an example now of that same IV bolus model, but now written for the PredBP subroutines. Now this is a case where you don't get that much of an advantage of using PredBP because there's no multiple dosing, but it still makes sense to view this now because it helps us to differentiate the different types of events, which we'll need to use when we go to the multiple dosing scenarios and more complex PK system models. So the same thing. Now we have an IV bolus dose with observations following 2 and 6 hours post-dose. We'll see how it's a little bit of a different structure now. We have 3 records per subject, but each one takes on a different value. Now the ID one at time 0 has an amount of 100 milligrams, and the DV here is just a placeholder. You could use a period or a 0 for that, because this is a dosing record. There's no observation on that first row. However, the next 2 rows are observation records at time 2 and 6 hours post-dose. You see that the amount column now is a placeholder. There's nothing there, but the dependent variable is filled in with the observed value of concentration at those time points. ID number 2, same idea. We have a initial dose at time 0 of 100, and then at elapsed times 2 and 6, we have dependent variables. So you see, again, the contiguous grouping of the IDs, now the sequential sorting of time within ID, and then the different records for dosing and observations. We didn't include the event ID here because it will be imputed by default by NMTran. Event ID will take on a value of 1 for this first row and a value of 0 for the next 2 rows. Remember, 1 is the event ID for an observation, and 1 is the event ID for a dose, the first record, and 0 is the event ID for an observation. Okay. So those are a couple of simple cases. We can get a lot more complicated with the types of data inputs, and I've got 3 more examples here that illustrate different data features within the NMTran system and grow in complexity, and we'll step through each one of these. But I just want to take a minute to remind you that there are several reserved data item names, and here's a list of them. It may not be even complete now with NonMem 7, so I'd ask you to check the help files if you're going to create a user-defined data item label that you might suspect would conflict with a reserved data item. You can check the help task on data items. There are also some reserved parameter names, which we'll talk about in the next couple of weeks, such as PK parameters, clearance, volume, Ka, the scale, the bioavailability, and so on. These are names that you should not use as well. Now, the nice thing about it is that user-defined data item labels in NonMem 7 now can be up to 20 characters long, but they must begin with a letter. Now, this is a big advancement over NonMem 6 and earlier. In NonMem 6 and earlier, the data item name could be no more than 4 characters. And so that really made it difficult sometimes to include multiple predictors that had similar names. You had to be quite creative with the way you use those 4 characters. But now you've got 20 characters long, and that's much more closely related to potentially the variable names that you're going to be using in your clinical data sets. That also makes it easier for the user-defined items to avoid conflict with the NonMem recognized values. The reserved data item names are all following that 4-character limit. So if you're creating a user-defined label, you'll know it'll be unique if you just at least use 5 characters. All right, let's look at another example. This is now, again, and throughout here, we're going to be continuing to use NMTran datasets for PredPP models. So we're going to take advantage of the recursive prediction and also some of the shortcut data items that we're allowed to use. Now we're going to specify a multiple dosing system. This is multiple oral doses, 30 milligrams every 8 hours for 2 days, with observational like PK sampling, sparse sampling. Okay, not a specific nominal time profile. So in order to do this, we're going to introduce 2 new data items. One is called ADDL and the other is called II. ADDL indicates the number of additional doses in a multiple dosing scenario. So, for example, if you had a total of 6 doses over a period of time, you'd have the initial dose plus 5 additional. So ADDL would be 5. ADDL does not represent the first dose, it's just what happens after the first dose. So always think of it as the additional doses. The interdose interval is the amount of time that elapses between those additional doses. And the units here are the same scale as time. So if your time is in hours, your interdose interval is in hours. So how do we implement that here? We've got one dosing record now to specify all 6 doses. We've got the first dose plus 5 additional ones. And the observation times are elapsed times from the start of the study, not elapsed times from the most recent dose. So let's review. Again, the column here at the beginning is the comment column. That's not required but can be useful. Right now we just have a placeholder there. We have 3 records for ID 1 and 3 records for ID 2. The first record here, is a dosing record. It represents that at time 0, a dose of 30 milligrams, I think we're using here, is given. And we'll skip the next 2 columns for a moment. The dependent variable is missing here. There's no dependent variable because this is a dosing record. And the individual's weight and creatinine clearance are also included here in the data set. But this record does more than just specify that first dose at time 0. It also specifies that 5 additional doses, for a total of 6 now, 5 additional doses will be administered every 8 hours starting after this first dose at time 0. So then at time 8, 16, 24, and so on, there will be additional doses. You'll notice we don't have to code all those additional dose times. We just know that they're taken on a regular interval and they're anchored at the starting time of 0. And so when you move along here, we have observations at 18 hours and 23.8 hours. Well, what's happened between 0 and 18? We've had, in a 8-hour dosing interval, we've had an additional dose at 8 and 16 hours. So 2 doses have occurred between these 2 records. We don't need to code them, though, because they're already included in the ADDL item. And so that the 18-hour observation is referring to 18 hours since the start of the first dose in this multiple dosing record. Again, 23 hours is 23 hours elapsed from time 0, from the first dose. Okay? The covariate effects here, you see them listed over time. And in this particular individual's creatinine clearance has fluctuated here, probably measured again here on the second day. Dropped to 70. In this individual, it changed a little bit. And we can record those time-dependent changes as they occur in time. We'll discuss what happens if there are large time gaps when we discuss the best practices later. Individual number 2 has the same setup. Single dose of 30 followed by 5 additional every 8 hours. Okay, so you see how this follows along that same theme. Every cell has its own value. Rows are ordered chronologically in time. Records are contiguous within each individual, and each record represents a single type of event. Event ID is not specifically included here. We'll take the default values. Again, for the first row, event ID would be 1. For the 2 observations, event ID would be 0. You know, and as I'm walking through these, I'll be looking over at the chat box too on the GoToWebinar control panel. So if there are questions that come up, please don't hesitate to add them there. Example 4 is a slightly different implementation. We're going to have to deal with a couple of additional data items. This is a steady state constant rate infusion, and we know that the rate here is administered at 10 milligrams per hour. We've got a PK observation at end of infusion, so after steady state's been achieved. And then a second constant rate infusion. This is an intermittent infusion. It's at 20 milligrams per hour, so it's a higher rate. And it starts 4 hours after the end of the first infusion, and it lasts for 2 hours. It's really sort of a short infusion here. And then we have a PK sample at the end of that second infusion, then 6 hours after the start of that infusion. All right, so sounds a little bit more complicated here, but it might be typical of an inpatient setting. And it would be kind of cumbersome to try to calculate the steady state conditions. But what we're going to use here are some of the built-in data items that link the data set with the model prediction with PredPP. And those include steady state, SS, and rate. So the steady state data item is really handy. This is one that allows us to bring a system, or the initial amounts of a system, up to some steady state level. So if steady state is coded as 1, that's indicating that the dose is a steady state dose. Whatever the initial amounts were in that compartment are set to 0, and now a prediction is made at the steady state value under the dosing regimen and under the assumed PK parameters. So recall that the steady state data item is telling you what's happened in the past. And so the steady state dose tells you that you're currently now up to steady state according to whatever dosing regimen you specify in that record. Now you can use actually a combination of steady state records. That's steady state 2, where you have a superposition of steady state doses. So it's possible to include sort of simultaneous steady state inputs, maybe at different intervals or different rates, and there's some utility in doing this if you need to achieve steady state on an irregular type dosing interval, but we don't use that all too often. The difference with steady state value 2 is that steady state dose doesn't reset the initial amount. It just adds, through superposition, it adds whatever the steady state amount would be to whatever was already present in the system. And then if it's a null value, a period, or a 0, that means it's a non-steady state dose or a non-dosing event. So we need the steady state data item for this problem because we have a steady state, we have two steady state, we have one steady state infusion, one steady state infusion and then a second constant rate infusion. Well, we also need to specify the rate. For the steady state infusion, we need to know the rate of input. And for this intermittent infusion, we also want to specify the rate of 20 milligrams per hour. So in order to specify a rate, we can simply include in the data set a number greater than 0. That's the rate in mass per time. So if our units are milligrams in hours, we could put a 10 for the steady state infusion, and we could put a 20 for that intermittent infusion. However, we can also now tie rate back to the model estimation problem. And this is kind of useful, but sometimes we might want to estimate the zero order input rate. And so if we use a -1 in the rate compartment, that tells us that there's a zero order input, but we don't know the rate. And then we'll have to estimate a related parameter in the model. Similarly, -2 allows us to estimate the duration of an input. We might not know the rate or duration, but we would try to estimate it, given that we know the amount that was entered. And again, if it's a null value, a period, or a 0, that means that it's not a dosing event, or that it's just a bolus dose and the rate doesn't apply. Okay, so we need these two items here to work on example 4. We have a PredPP data set. And by the way, you'll see here the file names. I have a zip file on the course materials site that has all of these examples as comma-separated text files. First, we're starting with a steady-state infusion. Now, this is the one sort of dosing record where time indicates the end of something. Okay, steady state, remember, tells us about what happened in the past. We're now at steady state according to some input record. So for this first record, we see ID1 at time 0. At time 0, we are already at steady state. It's a steady state dose at a rate of 10 milligrams per hour. Okay, 10 per hour. So in this case, we don't really need amount, and this is the only example of a dosing record where amount is 0 in NM trans system, and that's where we have a constant rate infusion. It doesn't really matter what the amount is. All we need to know is what the rate is to determine the steady state concentration. So at time 0, where this individual 1 is at steady state on a rate of 10 per hour. Then there's an observation at the end of that infusion. So this constant rate infusion stops at time 0, and there's an observation at that current time point. Then at 4 hours after the termination, so time 0 is the termination of the steady state input, there's a new dose. Now, if the rate was 20, let's go back to our specification here. The rate is 20, and it's going to last for 2 hours. So what's the total dose? 20 times 2, we're going to need a total amount of 40 milligrams. So our dose is 40 milligrams, and our rate is 20. Given those two, NM trend can calculate the duration, which is 2 hours. Okay, so it's at 4 hours post the end of the steady state infusion, there's a dose of 40 at a rate of 20 per hour for a duration of 2 hours. And then at the end of that time, 6 hours later, or I'm sorry, at time 6 hours, which is 2 hours later than the intermittent IV infusion, you see that there's a concentration observation, and then there's one 4 hours later at time 10. So this is a little more complicated now, but it still illustrates a few important points. Okay, number one, we still have different events at each row. We have dosing events, observation events, and so on. But it also illustrates that we can have two events happening at the same time. The first two records here happen at time 0. They're separate and distinct events because they're coded as separate records. And actually the way that these calculations are done is row by row. And so the order of these is quite important. The first row here is the steady state record, which brings the system up to steady state. And that's important because we're making an observation after that steady state input has occurred. Then the next row here, even though it's also time 0, it occurs, infinitesimally small interval of time after the completion of that steady state input. So you can have events at the same time, but the order of the record determines the order in which they will be implemented in the prediction model. Okay. Any questions on that so far? Okay, one more example. And this one's kind of intentionally complicated just to illustrate a few more of the features. But it's not something that you might, something you might see, at least parts of this, where we have a crossover here from oral to IV, or more commonly from IV to oral. But maybe somebody's entering the clinic here after being on some oral medication. I'm telling you about the model here because this is important in specifying dosing and observation records, and you'll see why in a minute. It's a one-compartment disposition. We are going to initialize steady-state oral dosing, 50 milligrams every 12 hours. We got a PK sample at the next trough. So the person comes in to the clinic here on a steady-state regimen, and there's a sample taken at the next trough. The next oral dose was observed, and we are actually going to use the observed time for that, with the PK sample following, and then an IV bolus was administered after that. PK sample is taken after that IV bolus, and then the additional thing we'll illustrate here is that the data are collected as calendar date and clock time. So this sounds a little bit complicated, but but we can handle this with the NMTran data specs. First of all, we need a new data item here, which is the CMT, or compartment data item. This is important in this model because we have observations which are happening in the central compartment, but we have oral dosing in a depot and IV dosing in a central compartment. So we have to specify where each one of these types of events is occurring. And so the compartment item allows us to do that. If compartment is 0, it's automatically assumed to be the output compartment, which we might use, for example, to collect urine data. If it's greater than 0, that's just the compartment number. So the number to which any particular event is occurring, the dose, the observation, the reset, whatever. And if it's less than 0, it's or a negative compartment number. The integer component specifies the compartment, and negative specifies a reset. So this is a way to give a reset to a single compartment of the system rather than resetting the entire system. We're not going to discuss this in a lot of detail now, but just for example, if you're modeling input from a transdermal patch, and you've modeled that patch as a depot compartment, oftentimes in transdermal systems, you'll remove the patch before the entire drug reservoir has been emptied, and so there's some remaining drug there, but there's a patch removal time. Maybe it's a 3-day patch, a 7-day patch, whatever. So you can use the compartment item here to essentially simulate the removal of the patch by setting that compartment to 0 without turning off or resetting to 0 all of the other compartmental values. So that's when you might use the negative compartment. Otherwise, we won't use this a lot in straight PK models, but when we have multiple input sites here, like oral and IV, it's required. NMTran will impute the default compartment value for most of the PredBP model libraries. So again, if it's an oral model library, the default would be the oral depot. If it's an IV model library, the default would be the IV central compartment. Okay, so let's see how we use compartment here. And I've got a picture to show you what we're working with here. Our model is a one compartment system with a depot and first order input. And the numbering convention used in PredBP and NonMem is that the dosing compartment is always number 1. So if we have an oral dose, that's compartment 1. The next compartment is the central. And we have an absorption rate constant, and then the ratio of clearance and volume for elimination here. But we know that there are different things happening in these two compartments. So that in compartment 1, that's where the oral dose is happening. In compartment 2, well, we have IV dosing, plus we also have observations. This is a central compartment from which plasma samples, plasma drug concentrations are representative. And so we need to specify the compartment associated with oral doses versus IV doses versus plasma drug concentration observations. And again, we can look at the PredPP guide for different structures here. We'll discuss that in more detail in the coming weeks. The other tricky point here is we're using date and time together. Date and time in the NMTran dataset will be transformed to an elapsed time behind the scenes. But we can specify the observations in terms of dates and times, clock times, rather than worrying about calculating the elapsed time. Okay, so let's take a close look here. Remember, we first said that we're coming in, this patient's coming in at steady state. He came in to the clinic on October 20th, 2001 at 8 a.m. This is 24-hour clock time. With steady state dosing here, 50 milligrams every 12 hours. That's the interdose interval. And we're at steady state. So at this point in time, the system's at steady state on this particular regimen. Those doses were administered, those were orally, so they're administered to compartment 1. And we're just carrying the person's age here as a covariate. That's not important to the dosing, but just to illustrate how the covariate can be included. Event ID would be an event ID value of 1 for this record. So that's the initial stabilization or the initial steady state system. And this is where we happen to observe the person is at 8 o'clock on the 20th, but they're already at steady state. Okay, then we've got an observation at some time here, some elapsed time. This happens to be on the same day, but at 1900 hours, 1952 hours. So about 8 p.m. There's a concentration observation. The difference here is that the concentration is observed in the central compartment. So CMT is 2 now. If you look at our diagram, CMT is 2 for the observation. Okay. Then there's a single dose, oral dose, that's observed, and they happen to take this just a minute after that. So this concentration was at trough. They take a dose of 50. It's not a repeated dose. It's not steady state. It's just an observed dose. So there's no steady state item. There's no II. But the time of that dose is recorded here at 1953 hours. That's an oral dose indicated by compartment 1 here. And again, carrying forward the person's age for maybe for use later as a covariate. That's followed up with a little bit later that same day, an observation dependent variable at 2200 hours. Again, that observation is taken in compartment 2. And then over the next day, so 8 a.m. the next morning, you see there's now the 21st at 8:06. There's an IV dose, same amount, IV dose of 50 milligrams, and it's IV because the compartment here is 2. It's also IV because that's what we asked for here. IV bolus dose at 12 hours after the last dose, remember that. So that IV dose is indicated by compartment labeled 2. And then that's followed by an observation about an hour later at 9:12 a.m., dependent variable of 150 in compartment 2. Okay, so this rather complicated scenario is pretty easily accommodated by just using the date time option, the amounts of doses, and the steady state and interdose interval factors, as well as the compartment. That's really the key here, is the compartment date item. So anytime you're going to have inputs in different compartments or observations in multiple compartments, you need to specify that. If that's not the case, you can assume the default compartments, and we'll review what those default compartments are when we start to work on the PK model structures. Okay, so those are the examples I wanted to use for illustration. We have a few other practice problems to work on, but we'll leave the practice problems for later. I'm going to pause for a moment and see if there are any questions on the chat. Pretty clear, I guess. Okay, well then we'll shift gears and talk a little bit about how we communicate the data items and the data contents to the model. And that's through the NMTran control records, $data, $input. So the instructions for NMTran related to dataset processing, they're provided in the control stream. Okay, so there are two separate files, right? There's the data file, the NMTran data file, which is a comma-separated or space-separated ASCII text file. And then there's a model specification file known as a control stream. That's also a text file. Within that control stream, there are two records, $data and $input, that allow us to define what's included in the data set and where the data set is and certain options. And what I've got here is listed some of the options. Actually, these are the NonMem 6 options. There's some NonMem 7 options that take this even further. that allow you to subset the data sort of on the fly. I'd encourage you all to look at the help item for $data as part of your homework assignment this week and look at all of the various options you have there. But here's an example of a $data statement. You might specify the name of the data file. Ignore equals C, that's just defining what the indicator is for comments, and so we use the letter C to comment, just like in Fortran. And although you could choose whatever character you'd like. And then the wide option here allows a particular format of the data. So that specifies the name of the file and some of the reading options. You can choose to rewind or not to rewind. You can subset the data on the fly. There's all kinds of neat features with respect to how NMTran reads your ASCII text data set. Coupled with that is $input. Now, $input is actually identifying what the columns are and what the reserved NMTran data names are in your data set. It allows you also to drop unwanted columns. You can use a drop statement here. And it assigns synonyms to data items if you'd like to redefine them. So here's an example, $input, and then you have here a label for each column in the data set that's entering. Some of these columns will be dropped, such as this one here, data equal drop. Some of them will be renamed. DV is being renamed to cunts, if you'd like to do that. And then others have specific meanings. So ID has a particular meaning, so do time, amount, steady state, II, compartment. But age, in this case, is a user-defined variable. It doesn't mean anything to NonMem until we actually include age as part of the prediction model. So this is really how we communicate what's in our ASCII text data set and the options for reading that. So please take a look at the help files and $input and $data. You can do that in the NonMem help available through the CIMI web interface that we've provided, or if you have NonMem installed on your own, you can look at your own online help files. But we'll take some time during the lab session to look at these in a bit more detail. So I've given you some rules and some examples, but sometimes there are points to consider or issues to think about that don't have a hard, fast rule. You just have to come up with a usually a reasonable implementation based on scientific logic or practical concerns. And let's take a minute to discuss a bunch of these here. Time-dependent covariates, missing covariates, the correct order of records, we already talked about that one, missing samples, missing dose times, missing observation times, and so on. So I'm just going to, I don't have a lot of notes on these, but I want to just point out a few things to think about. When you have time-dependent covariates, recall that, and I'm assuming here that we're talking about pred-pp, where time actually matters in $pred. Time, there is no recursive prediction, so time is not important. So time-dependent covariates, as we discussed, are implemented such that at current time record, time t, the values of those covariates are used to calculate the system concentration changes from time t-1 up to time t. So that it's a sort of a back propagation of those covariates. Well, that's okay, and it's usually not a big deal if your time intervals are not large and if the covariate effect is not changing very much. But let's imagine a hypothetical situation. Let's say we're dealing with a pediatric data set, maybe in neonates, and we're using body weight as a covariate. And we're following these critically ill children maybe for a month or two, from birth till a couple of months post-birth. Well, in that period of time, their weight can be changing quite dramatically, and therefore so can their PK parameters that might be dependent upon weight. If, however, that that individual subject is not followed on a regular basis with respect to dosing or concentration observations of a particular drug, there's not going to be a frequent sequence of dosing or concentration records. And so there might be gaps in time. Maybe there's a sample taken during the first week of life, and then nothing again until 2 months later. Well, that individual's weight has changed quite a bit over that time. And so the calculation would be done, of course, from week 1 up to month 2. The clearance would be calculated based on a weight that is equal to the weight at month 2. Remember, it's a backwards propagation of that time-dependent covariate. And so that can make a big difference in the prediction of concentration at that time point. So when you have these large gaps in time, and you have covariates that are changing, and that can be changing quite dramatically, such as in the case of pediatrics, what you might want to do is use the event ID 2, the other item, to insert covariate values over time, even though there might not be a dose or an observation taken, but to insert those covariate values over time to allow the system to more gradually accommodate that covariate change over time. And you can do that if it just so happens that the weights are observed on those days, or if not, you might want to use some sort of a linear interpolation to impute between week 1 and maybe week 9. So that's one thing to think about, is how to deal with time varying covariates. Most of the time we could just ignore the space between dose and observation records, but sometimes if it's a large enough gap in time and the covariate's changing dramatically, we should probably take steps to accommodate that. So there's no rule for that. There's just a point to consider. Imputing missing covariates is a similar thing. How do we deal with that? And really that's situation I just explained is a special case of a missing covariate. But let's say you have observation times where the covariate is missing. How do you deal with that? Well, if you have missing values within a subject, you might want to take the average of other values within that same subject. You might want to interpolate it over time between subsequent before and after covariate values. If it's entirely missing in that individual, you might want to impute them based on other values. So if, for example, weight is missing but you happen to have height, you might want to impute weight based off of the height-weight relationship seen in the rest of the population. Again, these are missing data issues that you have to think about. There's no correct answer, and oftentimes you have to make assumptions here, but it's something to think about as you're pulling data sets together. And you might want to construct them in more than one way and see how sensitive these assumptions might or how influential these assumptions might be on the modeling results. The correct order of records when things are happening at the same time, I already mentioned that. You can have events happening at the same time, but it's the order that they appear in the data set that really matters. Missing samples, missing dose times, missing observation times, these are difficult to deal with. And sometimes you might base missing dose times or observation times on a per protocol definition. Other times you might elect to eliminate observations associated with these. Missing samples, depending upon the reason, you might want to still capture that time point. For example, if it's missing because it's below the quantitation limit, or missing because a subject dropped out, these are missing data problems, and there's a whole literature on how to deal with these. But just ignoring them may not be the best route, and we talk about some strategies for dealing with these types of data sets in the MI210 course. But again, these are issues that have to be considered at the time of putting the data together. And it might be a good idea to just capture the time that the sample was supposed to have occurred, or the time that dose was supposed to have occurred, so that at least you have a full data set. You can always comment out those records later on. Okay. Well, where do you define these things, and how do you think about that? Well, one of the ways that's useful for me is to write a specification plan for the data, and you can include your plan for dealing with all of these assembly issues in that data specification document. This is useful if you're handing over specs to a data management programmer to create your NMTran data set, or even if you're doing the data set assembly yourself, just to get some clarity about how the pieces fit together, what it's going to look like, what are the assumptions you're going to make. And useful practice here is to create a data specification document. It also allows you to specify ahead of time how you're going to handle data problems. One of the things we do in this is to link the NMTran data items to their source database data set names and variable names, and also to specify the format of the NMTran data set. It's useful sometimes to specify plausible ranges of values too. You can use those for edit checks later on as a quick screen, and identify special instructions for creation of that data set. So I'm going to blow this up a little bit here. This file I've also included on the shared site, on the collaboration site, in an Excel format. I'll just scroll over as we get to this. And you're welcome to use this for your own work. But what I've done here is I've sort of mapped what I want to end up with on the left-hand side here. These are the data items in my NMTran data set. Next to that, I've got a description for each one in English, and then units. Sometimes units don't apply, but if they do apply, what are the units? What's the original name in the source data? Okay, so these are the variable fields in the source data, and then the source data file name. Sometimes you can map this back to different data files. You often have data files for PK observations, dosing, demographics, and so on, and so you can map it back this way. The format, is it an integer? Is it a clock time, calendar date? Is it a decimal, continuous value? And these again are useful just for checks. And then ranges, plausible ranges. So IDs here, we're going to range from 1 to 450. That's how many subjects we have in the data set. Clock time shouldn't exceed 24 hours. This is also just a useful check. And then defining are they continuous or they categorical. And if they're categorical, how many levels do you expect? 5 categories of event ID, 3 categories of type, which is just a user-defined value, and so on. So this is a nice way to map those, and then you can include a comment field too. So defining, if you have 2 types here, male, female, non-smoker, smoker, or if you're going to calculate using a particular formula. And I'm not saying that everything is here. There may be fields or descriptors that you might want to include, but you could use this as a starting point. It's just a useful way to map your data assembly plan back to the source data. Now I've got some notes here. You can include notes, although sorry about that, there's a typo here. But some of these notes, will tell you backfill covariate values when changing over time, assign event ID 2 or amounts 0, and DVs are 0. So those might be missing values. Use separate records for each event. Just the general rules here. But if you're communicating this to a programmer, it's pretty helpful to do something like this. Okay, and as I mentioned, this spreadsheet here is available for your use on the shared site under this week's lecture material. Okay, other things to think about. After you've written this plan, you've thought about how to handle these data exceptions, and you communicated that, and now you have an NMTran data set. Then it's useful to create some diagnostics. And one of the things that we typically do is create index plots, where you graph all the data items versus ID. This is just a quick way to identify errors in the data, obvious outliers, It's not going to tell you the fine detail of where there might be errors, but the gross mistakes you can see pretty clearly here on these index plots. For example, if everybody had dosing between 0 and 20 milligrams, and all of a sudden you do an index plot and you see somebody with a value of 2,000 for a dose, you know that's probably a data entry error. You can quickly pinpoint those. You can plot the data, the dependent variable versus time, with ID as the label. Plot histograms of the continuous data items to get an idea of the distributions. Box plots of continuous by categorical. Correlations as well between continuous and between various continuous endpoints in your data. And then summary statistics of the NM-Tran data items. And you can compare those summaries like the mean, the variance, and so on. Compare it back to the original source data. Now they might not be exactly the same because you might have eliminated a data record for one reason or subsetted, but they should be useful as a reality check to see if there's any gross errors in your data assembly. So those are useful things to do. You need to also think about maintaining a data assembly audit trail, where really what you need to do is trace your final data set back to its source, and to be able to reproduce that data set assembly. These are requirements under regulatory environments for data assembly. That's also just good scientific practice. And how do you do that? Well, one is you could do keep good records and make manual data manipulations, but that's kind of tough and not so reliable. And so I'd highly recommend that you use a programmable data manipulation tool. There's a variety of them available. The one that we're going to use, actually I didn't include in the list here, but is R, and we'll review some data assembly together here in the course. I'd point out that we spend a lot of time talking about this in our course on R programming, which is a separate course. But this is really the way to go if you're going to be doing this work on a regular basis in a production environment. You need a programmable data manipulation tool. And then just a few things to think about on data management. So if you get involved in defining data specs, case report forms, databases, and so on, some obvious things here, but the source data files should always link to all data associated with ID, date, and time. Study day is not always a reliable thing because sometimes study day in one field might be a different value in a different field. For example, starting at 0 versus starting at 1. And so date and time are much more reliable. Source data sets should use the same names and units across multiple data sets if possible. If you're going to have creatinine clearance appear in more than one place, or subject ID or treatment code, hopefully they're mapped the same way. Unique identifiers should link each sample, whether it's PK or PD, with the study, the subject ID, calendar day, clock time. It seems obvious, but sometimes we end up with data sets where there's all these nice PK samples taken, but there's no record of what time they were taken or what visit they were taken, and so they become much less useful. Dose amounts, dates, and times should be recorded in the CRF entry and end up in the database. So anytime, that's the easiest way to map things together, is using dates and times. And then carrying duplicate information in the database and the case report forms. That's a risky thing to do because oftentimes you may end up with discrepancies, and then which one do you believe? So capturing demographics, baseline demographics in one place is probably good enough. And so these are things to consider if you happen to be involved in the design of case report forms or data sets, or if you're asked for input on those related to population PK/PD work that you might be doing. These are some things to think about. So for help on these, I mentioned that you should see the NonMem help items on $data and $input. I'm also going to put a plug-in for the MIfuns R package. We're going to use the MIfuns package throughout this course. This is something that we developed here at Metrum Institute. But in our practice, we've developed several useful functions for simplifying the data assembly process. And I'll show you a couple examples of that, although this is not intended to be in our course. We'll have them scripted out for you as we move through the course examples. But if you're interested in learning more about this, I suggest that you consider taking the MI205 course, which is our programming for pharmacometrics. I know that some of you already have taken this course. It was formerly called MI220, same course. But that's a useful way to do some data assembly, and we're going to take advantage of those tools in this course too. Okay, you've got some homework problems. And these problems you can do just using a spreadsheet. You can do it in Excel or something like that. Don't worry about the specific values for covariates and dependent variables, but I want you to get some practice in creating NM-Tran data sets. And we're just going to use a subset. So the first one is create a data set for 2 subjects. Multiple dosing, in this case, PK sampling after the first dose, last dose, and arbitrary values for concentrations. Now I've got you set up problem 1 and 2. It's the same problem except for the last line. $pred model with no pred PP library. And number 2 is to use the pred PP library. I'm going to give you a break here, and I think we'll skip problem 1. Skip problem 1 and focus on problem 2, which uses the pred PP implementation. This is how we're going to be coding multiple dose PK anyway. I think we've already spent enough time discussing the differences between the two. So skip problem 1 and focus on problem 2 for this week. And then we'll also add problem 3. This is a hypothetical study, a little more complicated. We've got multiple dosing, 200 milligrams every 12 hours. We've got an IV infusion. I'm giving you some more information here too about a change in dose depending upon response. We've got PK sampling after the first dose, telling you that it's a 1-compartment model, so that's hinting that we're going to have to consider compartments as we're pulling this data set together. And even half-life here. Half-life, why would that be important? Well, it might influence our assumptions about using the steady-state dosing item. Covariates are included. You can make up the values. I just want to see you try to put covariates in there. We're going to use the pred-PP model libraries. And so create a hypothetical NM-Tran data set for 2 subjects. Okay, so there's 2 examples here. It'll give you some practice. In addition to this, if you have your own data sets that you want to start working on, you could use those as well. And that's going to be as we introduce the project for the course, that'll be part of that, is to create a data set. So the more practice you get, the better. But let's try problem 2 and 3 for this week, plus some study guide questions. We'll review those at lab on Friday. We can also, if there's some related questions, I can also address those through the discussion boards between now and then. Okay. So just to remind you, I'll point out on the discussion on the classroom site, you have here the course notes, of course, and then the examples, which include the data specs document and the comma-separated CSV files for examples 1 through 5 that we ran through in class. You can use those as a starting point for problems 2 and 3 that you're going to do for homework. I'll post the solutions to those after Friday's lab. So before we wrap up today, I'll pause for any questions. Sounds pretty quiet there on the chat board. So we'll wrap up today a few minutes early, give you a chance to get started on some of the homework problems, and we'll meet again on Friday at the usual time to review those problems. Thanks for your attention, and don't hesitate to contact me if there are questions between now and then. See you on Friday.